Welcome to Energy Talks, a regular podcast series with expert discussions on topics related to power system testing, data management, and cybersecurity in the power industry. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Hello, everyone. It is never too late to make New Year's resolutions. Maybe this is the year that you learn more about partial discharge testing and even begin to regularly use it as a diagnostic tool to assess the installation condition of your electrical equipment. Partial discharge, or PD, is a reliable indicator and major cause of electrical installation deterioration, which can eventually result in equipment failure and costly outages. With me to talk about the essentials of PD testing is Casper Steinecke. He is an Omicron PD expert and co-developer of Omicron's MPD, PD measurement and analysis technology. Casper is also the PD expert featured in Omicron's video series called The Essentials of Partial Discharge Testing, which you can watch on YouTube. More information is available in the text description accompanying this episode. So without further delay, hello Casper. Welcome to Energy Talks.
Hi Scott, thanks for having me.
It's great to have you. Casper, please describe your background in partial discharge testing.
Well, I studied and worked in research at TU Berlin, the Berlin Institute of Technology, and originally we were doing research in frequency variable dissipation factor as a diagnostic tool, the so-called VLF tech. Then, with that, we started a company. We made a foray into medical instrumentation and some space technology. We then returned to partial discharge. That had always been our interest. And this was really prompted by some very specific needs that arose at the time, and that could not be met by existing instrumentation. And these were the first extra high voltage XLPE cables going into operation. And then we had cooling water pumps in nuclear power plants, where these are located in a hot zone that's only accessible every few years. And then you had to have instrumentation that would meet certain stability criteria.
Interesting. So, Casper, what exactly is partial discharge? What does it indicate?
Well, partial discharge is a localized dielectric breakdown. So when you have an insulating system, it's a small discharge within the insulating system that does not result in a complete flashover. So there's no complete bridging of the insulating system, no total failure, but rather it's very, very small discharges, and those indicate defects or weaknesses in the insulating system. And as we all know, insulating systems determine the lifespan of electrical energy assets. So there is a destructive potential for these small defects, and that's really measured by the charge involved in this particular event of partial discharge. So it's a very good and interesting measure to look into aging and damage processes within electrical energy assets. And it's really important, and we'll come to that later, to understand the difference between detecting and measuring partial discharge.
Okay, interesting distinction. So how harmful is partial discharge activity in electrical equipment?
Well, that really depends on the type of insulating system and your particular electrical energy asset. So for some, like rotating machines and generators with micro-insulating systems, some PD is completely benign and it's totally tolerated. It's a normal part of operation. For XLPE or resin assets like, let's say, cables or cast resin transformers, that's where we want absolutely no PD in an ideal world. And yet for like oil in transformers, particularly large power transformers, we're really a lot more tolerant. So PD is, again, part of the process, but it should be within certain limits and bounds.
So that's an interesting point. When exactly does partial discharge activity threaten electrical equipment?
Well, PD leads to a localized destruction of parts of the insulating system. So in particular, organic dielectrics. So let's, for example, look at XLPE or resin, where you have the decomposition of the carbohydrates that this is made of. And this results in a growth of tree-like channels in the direction of the electrical field. And if these channels then eventually become longer and bridge the insulating systems, that's when you get a complete failure and a flashover, and that's the total destruction of your asset. So that is particularly dangerous. In oil, like in transformers, oil-filled transformers, it's different in that you also have a carbohydrate, the oil, but when you have discharges, so it's local arcing, and then that arcing leads to a decomposition of that carbohydrate, and you get gases as a result. You can measure these gases. You can look into the gas content of your oil, and that is an interesting indicator, in fact. But again, you're a little more tolerant in transformers, as some would consider oil-filled acids self-healing. That's something you sometimes hear. It's not actually true, but to a certain degree, when you have a local defect and then it gets filled up by oil, that is to some degree self-healing, yet there is always damage. In mica insulating systems, so we're talking generators, rotating machines, large motors, that's where you have PD as a very normal part of operation. But even there, if you have strong PD, or PD, rather large swings in PD activity, PD suddenly getting a lot stronger, then that is also an indicator of a localized failure. And then that's something that we definitely want to look into.
You had mentioned before that PD occurs naturally in electrical equipment. What exactly causes partial discharge in electrical insulation?
Well, as I mentioned initially in the definition of partial discharge, it's a localized dielectric breakdown. So whenever you have a local field strength that exceeds the strength of the insulating system, then that part of the insulating system will break down. And that's when you get partial discharge. And this can be, different depending on the insulating system that we're looking into. Let's say you have an imperfection in an XLPE insulating system, that is a small particle that got in there somehow. Then along that particle, you might get a discharge. You might then get a defect that will eventually grow larger, or bubbles in cast resin. That's why all these cast resin production processes are so tightly controlled for air ingress and bubble formation. Any kind of pre-existing defect. Then in some insulating systems, it might be water ingress that causes humidity and degrades insulating systems. That's where you get eventual failure. And again, it's really interesting to do PD testing here because it's such an early indicator. It provides information typically long before anything serious happens. And so, especially for these kind of developing defects, that's really interesting.
So that actually answers the next question I have for you. Why are partial discharge measurements a critical diagnostic tool for electrical equipment?
Well, yeah, as I mentioned before, it's the insulating system that really determines the lifespan of electrical energy assets. So what kind of predictive diagnostic tools do we have for that? Not so many. We can do integral measurements that diagnose overall aging. And the prime example here would be 10 delta dissipation factor. So dissipation factor is really interesting, and it's good for diagnosing and testing for general aging. And you will typically see the dissipation factor go up over time, but the dissipation factor will not register or detect an individual defect, typically, with certain exceptions, but mostly it will not. It will provide an overall aging parameter. But if you have an individual defect, then PD is pretty much one of the very few, if not the only way to have an early indicator of that.
Okay. And so you're saying that partial discharge measurement is more of an exact form of determining whether you have a defect that could lead to an eventual fault.
It is in particular an early detection. Since we're measuring a very small partial breakdown of the insulating system, we have an early indicator of something much bigger that will likely happen in the future.
Okay, so that gives you time to take corrective action if needed.
Exactly. It's early indicators that are so important for directing maintenance resources, for example. I mean, you have, like a whole range of energy assets that you're looking after. Well, which one do you do first? You can go by simple schedule and, exchange them every so many years. That's not so much an option these days anymore. And resources for maintenance are typically scarce. Then you have long delivery times on assets. So you want to direct those scarce maintenance resources to where it really matters. And that's where PD is so important.
What are your repair possibilities and what are you actually doing if you find a defect?
Oh, wow. That's a long question with long answers. It really, really does depend on the asset. There are assets that are perfectly well repairable and where you can do even localized repairs. And then there are assets that you simply replace. So you will not be able to repair an XLP insulating system or do a lot of repair on a cast resin transformer. But on large oil field transformers, especially large power transformers, you certainly do repairs if it's worth it. And also on rotating machines, repairs and redoing parts of the dielectric system are absolutely a possibility.
So you mentioned that there are some assets, such as a high voltage cable, that are not repairable, but at least the indication gives a fair warning that a failure could eventually occur.
Yes, well, they're not repairable, but they're locally replaceable.
Okay.
You wouldn't replace a very long cable in its entirety, but you would remove and replace a section. As and then with cast resin transformers, those are typically less expensive and they're used in smaller substations and in distribution. And so those are not very painful to replace, but they might be very painful if they fail. Sure. Especially when they power very critical processes, say data centers or industrial production. So criticality is really important.
Okay. So again, you partly answered my next question. What types of organizations are involved in PD testing?
Well, PD testing, first of all, happens when electrical energy assets get manufactured. Mm-hmm. So they're typically part of the quality assurance process. They also really help in optimizing internal processes. So if you manufacture something, then PD provides critical information on the quality and performance of your processes. That is internal feedback even. But then typically your customer, and that's the next step, will ask for some kind of PD testing certification and that you can provide alongside with the asset as you deliver it. And then that customer will want to commission that asset. And so it's transported on site, a lot of connections are made, and then it's time to test again. So that's when the next PD test is performed during commissioning operations. And that's a very important application. It's, in fact, the application that led to the development of that MPD technology. And then once in operation, you might want to perform regular testing. This is part of your asset management process, especially when you look into more critical assets, as I mentioned before. So if you have, very high criticality for an asset, you might even consider permanent monitoring for PD. So all of that is an option. And then you do So regular testing or permanent monitoring. Again, as I mentioned before, for directing limited maintenance resources, it's also to ensure very high reliability in specific applications. And then, of course, you ask for organizations. So then, of course, you have standardization bodies as well. So there are certain standards that apply to PD testing, and these are worked out in working groups. Then there are national standardization bodies and international ones, like IEEE or ISO. And these are in a permanent process of evolution. And there are standards that apply to PD instrumentation. There are standards that apply to PD testing on specific assets like cables or rotating machines.
Who exactly performs partial discharge measurements in these organizations?
Well, that is typically, the responsibility of engineering and maintenance crew. So some organizations do that internally. Others will task service providers with that. So we have testing labs, independent testing labs, as well as industry or utility testing labs.
Very good. So do you think there should be more awareness about the essentials of PD testing in such organizations? And if so, why?
Well, first of all, there should be a general awareness that PD is an available tool. It's a tool to improve your general asset management and your awareness of the resources that you're deploying and that you're looking after. So in addition to that, then of course, you have the engineering and maintenance people, and those definitely need more specialized knowledge of these testing processes. And again, these can be very simple, general tests that are routinely performed, and you can relatively quickly train people for that. Or you can have a resident expert that typically has very specific asset knowledge and then uses PD as one of the tools in his or her toolbox.
How often should partial discharge measurements be performed on electrical equipment?
Yeah, it's a good question. That's actually highly asset dependent. And of course, dependent on the criticality of those assets. So, while some assets like cast resin transformers are remarkably reliable and resilient, you should still test them and even monitor them when you have them in very critical roles, like powering a data center or powering critical production processes. You would certainly not do this on a residential distribution transformer. So it's criticality, and then of course it's the type of the asset. So for some assets where, you have, let's say, extreme load cycles, let's say you have a large motor in a mining operation, it might be interesting to monitor that because it has sometimes extreme or unpredictable load cycles. And you want to look after that more often. If you have assets that kind of, perform typical roles in a very predictable manner and are not overly critical, then you might want to do a measurement every year or 2 years or a few years. And on others in industry, you might want to do this every few months. And on the very critical ones, again, you might want to monitor them permanently because they're so critical for your operation.
Okay, so you mentioned the frequency of the measurements. What is the benefit of comparing the results of regular measurements?
Well, when we're talking about assets operating on site, then it's difficult to reproduce the standardized testing conditions, that you have when those assets were manufactured. So you're looking at a less than ideal testing situation. And when you have less than ideal testing situations, let's say, with a degree of external interference or limited means to calibrate your measurement, for example, that it really, really helps to look at a succession of measurements. Things change. And if things change a lot, then, that's sometimes reason for concern. So it's great if you do these measurements regularly and then see variations or worsening of partial discharge, for example. And then that might help you direct those maintenance resources and look at that specific asset.
Very good. So we've been talking about partial discharge measurements, but we haven't talked about how they are performed. Could you describe the process there?
Mm-hmm. Well, actually, a partial discharge measurement is pretty simple. You have to have a voltage, you have to have a means of decoupling from your test circuit, and then instrument. And it's pretty similar to testing a capacitor. You apply a voltage, you have some means of decoupling, and this can be a coupling capacitor, it can be a built-in coupling capacitance, as in bushings, for example, or a machine that's pre-equipped with couplers on the main power bus. And then, you connect an instrument to that, you apply voltage, and you take a measurement. It's really that simple. Of course, you might want to perform a calibration, so it's important to understand. Partial discharge is calibrated using pulse injection. So you have a small device called a calibrator. Take that, and that comes, with the instrument. And it's a small device that you use to inject pulses into your test circuit. And then you take a reading and adjust the system to that. It's really simple. It's a very quick procedure. The calibrator itself is traceably calibrated, and so it's traceable to national and international standards, and it makes measurements comparable. But of course, I should mention the MPD technology in itself performs an absolute charge measurement on the pulses that it sees. So, and it is highly stable over time. So even if you wouldn't calibrate, you would still see changes over time. But of course, you do calibrate so that you have a precise measurement of what's actually going on. But as I said, it's really simple to do a quick PD measurement. The real challenge is noise, always. Noise means interference. It means we're looking for very small discharges, and these very small discharges, if you have a very noisy environment, can be hard to detect.
And that's because the equipment itself is so sensitive that it's picking up not only the PD signal, but also the noise signals at the same time.
Exactly. And, a great deal of effort in creating the MPD went into technologies that discriminate noise versus PD and that help you evade that noise and make a perfectly valid measurement even in very difficult conditions.
Very good. What are some of these things that have been developed to enable that?
Well, first and foremost, it's optical separation. So we use optical fibers to avoid ground loops, to avoid picking up noise, and also to keep you safe when doing these measurements. And then we have filters. We have variable filters that help to avoid noise. Noise is typically, or most noise is limited to certain parts of the frequency spectrum. And if you can look at that frequency spectrum through, let's say, the built-in spectrum analyzer, and then select a measuring range that avoids most of that noise, then you're pretty good. And then you can, under most conditions, perform a decent measurement.
Okay, so you're actually adjusting the frequency to find that range where you have the highest signal-to-noise ratio.
Absolutely. Yes, you can change that frequency. And then we have a number of other technologies that would, for example, help us gate out, this is called gating, so suppress certain, let's say, pulses that do not represent partial discharge, but rather come from some external source, for example. Let's say some converter that's nearby and whose pulses then would otherwise disable the measurement, and we can suppress that if it doesn't cover the whole frequency or time range that we're looking at.
Okay. So you had mentioned before that PD measurements are actually easy to perform. What about the analysis of the collected data?
Yeah, well, that's basically two things that you need to distinguish here. So first of all, it's the intensity of partial discharge. Partial discharge is typically visible because it represents the highest, recurring pulses. Then they are synchronous to the incoming AC voltage, so the test voltage, and that makes them pretty easy to see. However, some PD is perfectly benign because it's caused by, let's say, external discharges, so-called corona, that typically does not represent anything dangerous because it happens on the outside. It happens on metal parts. When you're in a substation, it rains and you get a lot of corona. Now, what we're looking for, of course, is internal discharges that are destructive to the insulating system, that have destructive potential, and that will eventually disable electrical energy assets. So for those discharges, we're looking for specific patterns. And as a baseline, there are not so many different such patterns. So it's relatively easy to distinguish external and internal discharges. And then when you're really into this, and when you have a lot of specific knowledge about your asset and specific experience, then you can read more into these patterns and you can distinguish certain patterns representing certain defective modes of your energy asset. But the most important distinction here really is external and internal discharge. That's easy. And noise versus PD, and that again is easy.
Okay, with the tools that you had mentioned.
On a very basic level, again, you can do this without getting extremely deep into these tools.
Okay.
Then as you dive deeper, there are certainly a lot more things you can do.
And of course, that shouldn't scare anyone off from doing PD analysis, because the more you do it, the more experience you gain. And that puts you at that level where you can take that deeper dive.
Exactly. And, it's kind of like with smoke detectors. The most important part here is to detect smoke and ascertain that it's really smoke. And then, you can call in the experts that might then do a specific analysis of that smoke and break it down into individual gases and such. But as a basic test, that's not what you do.
Okay, I want to go back to a previous point you made when you made reference to the fiber optic cables that are used to reduce the amount of interference, for example. You had mentioned that it also keeps the engineer safe. How safe is it to perform PD measurements, not only for the engineer, but also for the equipment? Is it?
Yeah, there are different types of PD tests that you can perform. When you do initial quality assurance, then you might typically, and that's actually prescribed under some standards, you might do so under a higher than normal voltage. So the test voltage exceeds the nominal operating voltage. And that provides margin to your customer and, of course, also to your internal processes. So you know something about your margin. In typical on-site testing situations, you would not necessarily use a higher than normal voltage. So that is zero additional stress to your equipment.
Okay.
And for an operator, it's perfectly safe because the equipment is separated from you by, optical fibers that are insulating you, and you can literally stay away like tens of yards or meters from where that testing takes place. So there's no danger in that.
Okay. So going back to your distinction between quality testing in the factory and then off-site testing in the field, there's a destruction potential there. Generally, I've heard you say that partial discharge measurements are non-destructive measurements, unless you want to create a destructive situation.
Yeah, that is indeed true. And there's an interesting story to that. The MPD can record, MPD technology and MPD instrumentation is all capable of recording every bit of a measurement down to the last detail. And this is really important when you do a post-mortem, that is, when you've done a destructive test. We learned this originally when we did measuring technology for space applications, because that's a place where you can't really repeat measurements. That's way too expensive. So we learned to record every bit of our measurements for post-analysis back on Earth. Now, this is kind of similar to PD here. So when you have a destructive test, and yes, manufacturers absolutely want to do destructive testing because they need to know their margin. And I mean, this is not on a regular scale. It's like car manufacturers that crash cars. You want to know
how far you are.
Exactly. And so testing with voltages significantly higher than the nominal operating voltages is something that's frequently done with MPDs by manufacturers typically. And that's where this recording capability and post-mortem analysis is really important.
Okay. Just out of curiosity, let's say you have an intentional destructive test situation and the asset fails as a result because you put it beyond the margin and you want to know what those margins are. What about the equipment itself? Would that damage the measurement equipment?
No, typically not. No, I mean, these testing situations are pretty well controlled. You have a limited energy supply. So once you have a breakdown, then your source will typically switch off automatically during these tests. So there's limited energy available. You won't get the big explosion. It's typically just a thump that you might hear, but nothing really spectacular to look at. And, people working in that will know about that. And yes, there is a significant transient involved in such a failure, but we've added a lot of protection to the input of these MPD systems. We've got a lot of experience with pretty extreme situations here. If you really do heavy destructive testing, or if people do really heavy destructive testing, we ask them to talk to us about such limits. But in general, hundreds of MPDs are seeing destructive situations every day, and it doesn't affect them.
Casper, if you could offer any tips about PD testing to our listeners, what would they be?
Well, I'd say just do it. I mean, start simple. Do a simple PD testing situation to, get a feel for it, understand it. Take a basic measurement. Use the same parameters every time you take that measurement so that you get results that you can compare. Then learn the tricks of the trade. Take a class. We have an Omicron Academy. We provide classes and training. Talk to us, get literature, learn some more, but basically just do it.
Okay, good advice. Why will the future be even more important for PD testing, in your opinion?
That's an interesting question, too. First of all, there's a general tendency towards more and better organized asset management, and following from that, condition-based maintenance. So organizations tend to integrate these measurements with their asset management, and that increases the potential and the need for PD testing. And then, of course, grids are getting more decentralized, more complicated in a way. We have electrical grids that are operating in stress patterns that we haven't had before with decentralized power. So some of that gets us into new territory, unknown territory. And we need to do a lot more testing to make sure everything still works. And then we have advances in materials research that get designed into assets, but not translated into extra margin. So if we have better materials, it typically means, for example, thinner, lighter insulating systems. It doesn't mean extra margin because there is a certain acceptable failure rate, and the economics of the trade mean that this typically translates into more competitive on an economic scale equipment and not bigger insulating systems or not stronger insulating systems. And that in turn means that some of these quote unquote optimized insulating systems can fail quite spectacularly and make it even more important to look into them.
Casper, thank you for joining me for this Energy Talks episode about the essentials of partial discharge testing.
As always, a pleasure. Thank you, Scott.
Thanks again. And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, data management, and cybersecurity in the power industry, and offers you the matching solution for your application. For more information, be sure to visit our website at OMICRONenergy.com. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.